That's okay.
You may know. Okay, now I'm not as happy, but still we have. We have Rakesh Venkat from IIT Hyderabad. More importantly, he was a PhD student here for Prahlad. He's joining remotely. And today he'll talk about communication lower bounds for graph connectivity.
Yeah, thanks everyone. It's good to be back here after a break. So I'll be speaking on communication complexity of this problem called graph connectivity. And hopefully I'll be able to define everything to get everyone up. Okay. So I'll spend some time defining the problems, a reduction. I'll set the stage for our main result, which is actually the lower bounds.
Just make the statement thought. Also, just move the camera.
No. So I thought I would be there.
No, make sure you have it.
Okay.
Yeah, and the upper bounds will set the stage for the lower bounds, which is our main result. So let me start with defining the basics of the two-party communication model. You have two parties, Alice and Bob, or two players, Alice and Bob. Each of them get inputs. X is known to Alice, Y is known to Bob. We can think of them as some n-bit strings. And now they need to communicate in order to compute this function f that depends on both the inputs. Okay, and the goal is typically to minimize the total amount of bits communicated, at the end of which they will know the answer to whatever the function value is. So we'll think of the communication as going in rounds. So for instance, this protocol, Alice sends a message M1, then Bob looks at that, sends back a message M2, and so on. The message that a player sends, one sends any message that Alice sends, can only depend upon the input that she has and the messages that she has seen. So this is the standard two-party model. Okay, and a single transmission may consist of multiple number of bits together. Is called a round. We call it a round. So the protocol here, for instance, consists of R back and forth transmissions. So I will say this is having R. And the cost is, of course, the total number of bits communicated. So clearly there are two models, deterministic and randomized. In the deterministic case, we want a protocol which computes the correct answer on every input without any error. And the randomized complexity of the function f is the minimum cost in terms of the communication bits of a protocol that is allowed to err with probability at most 1/3 on every input. And where the players are allowed access to random coins, so they can carry out this randomized protocol. The messages can be random. And it's a well-known fact that the randomized complexity can be significantly different from the deterministic complexity for the same function. For instance, the well-known equality function determining whether the two strings x and y are equal or not has a randomized communication complexity of just constant, whereas its deterministic communication complexity is n, all the way to trivial. And in this talk, we'll be restricting to protocols which have only R rounds. And for that, I will use the notation D with a superscript denoting the number of rounds.
So one round for you is one message or one back and forth?
No, one round is one message. So here's the main problem that we'll be concerned about. Alice and Bob are given as inputs edges of an n-vertex graph. So the vertex set is, say, 1 to n. Right, and it's known to both players. The vertex set is common. The edge set is divided up amongst the players, not necessarily in this that it's a partition, but it could very well be. And the question is to ask whether the union of the edges together forms a connected. So it's a Boolean function. They want to determine whether the union graph is connected. So there's a simple one-round protocol for this. And the one-round protocol, let me be clear. Alice can send Bob a message, and Bob will know whether the graph is connected or not. So what is this one-round protocol? Well, notice that connectivity does not require all the edges. Right? Determining connectivity requires only order n edges. So Alice computes the connected components on just her edges. Okay, so this will take the form of spanning forest. It will have at most n edges. Right? And so she informs Bob of this spanning forest that takes n log n bits, right, describing n edges. And using that, Bob can just determine whether the edges that he has connects up the components that Alice has sent. And if it connects up all the different components that Alice has sent, it forms a complete spanning tree. Then Bob will say that the graph is connected, otherwise he'll say it's disconnected. So this is a simple deterministic protocol with a cost of n log n bits. Okay. Furthermore, it's just one round. A message from Alice to Bob, and Bob knows the answer. So what is known about this problem in more general settings? So the deterministic upper bound is simple. What about lower bounds? So if you look at just deterministic protocols, Hajnal, Maass, and Turán showed that you need n log n bits irrespective of the number of rounds. So even if you allow back and forth multiple messages to pass, you cannot improve asymptotically on the protocol that was discussed. Only one node. So that's kind of optimal in the deterministic setting. But what happens if you allow randomized protocols? In randomized protocols, for a one-round protocol, Sun and Woodruff showed a reduction from a variant of the index problem that any one-round protocol, even if allowed to err with some probability, will take n log n bits. It wants to compute the correct answer with constant probability. Whereas in general, if you allow any number of rounds, the best known lower bound for this problem comes from a reduction from the disjointness problem. The reduction was given by Babai, Frankl, and Simon, and the disjointness lower bound was proven by Williams and Raskolov later, that it gives a omega n lower bound. So disjointness is a well-known problem in communication complexity. It's a central problem, and just a reduction from that gives you omega n lower. So there's this gap, which is a fundamental open question. Is the connectivity problem, does the connectivity, is the randomized complexity of connectivity n log n, or is it somewhere in between n and n?
There's some more recent word that was some log n or something, right?
So I don't believe that for randomized connectivity,
maybe I'm not remember. Let's do on. I remember some things on the log, but it's okay.
yeah. So there are things that go to logarithm. For instance, you can think of connectivity as determining whether the min cut is 0 or greater than 0.
Yeah.
For min cut being a threshold t and greater than t, there's a lower bound of n log n. But the threshold t is not 0, some large number close to omega n.
Okay, maybe
and besides being a fundamental open question, it has been mentioned that it implies the optimality. A tight lower bound on the randomized complexity of connectivity implies the optimality of certain cut query algorithms. So this is the main problem that we want to. Yeah.
Are instances for this problem? Are they typically sparse graphs, or those graphs have to be dense?
So the graphs. So it kind of, so if you look at connectivity, it does not matter whether it's sparse or dense, because it's just maintaining connectivity. Right. On just,
yeah.
So the instances itself, for instance, Alice gets a set of edges, she could make it really dense or keep it sparse, the connectivity property would still be preserved. So that it doesn't really matter. But I'll come back to that in some other. There are instances.
And the proof techniques are progress to solve the or the techniques.
Yes, so this proof technique comes from a rank lower bound, but that works, I think, on the instances that you consider dense graphs. The deterministic lower.
Actually, I thought Manal's question was more like, are the hard cases like, do the inputs that Alice and Bob have, do they have like a lot of components, or it's a question of they basically have just 2 components and it's a question of whether Bob's edges, I don't know, maximum.
For component wise, I believe that they do have lots of components.
Oh, they have lots of.
Yes.
Yeah.
But yeah, the only lower bound that we know of properly is this, is a deterministic that it is. So what are our results in this? We first show that any two-round protocol that decides connectivity requires omega n log n bits of communication. So Alice sends Bob a message, Bob sends Alice back a message, and Alice knows the answer. So any protocol of this form should communicate at least n log n bits. And for any constant round protocols, we show a superlinear law. So this here is the iterated log. R is the number of rounds. So for constant rounds, this works. And this is an improvement over the previous minimum bound for these protocols. Okay. Although our main result is the two-round thing. The constant round, I'll mention how it follows by adapting some previous work. But in this talk, primarily, I'll be concentrating on the two-round law.
The iterated log is the same matrix law and pointer shape.
Yes, it comes from pointer shape. So how do we prove our lower bound? There's a well-known problem called pointer chasing. It's a many variants of this well-known, well-studied problem called pointer chasing. We show a reduction from one particular variant of pointer chasing to the connectivity problem. And our main technical contribution is a new randomized lower bound for this variant of pointer chasing, which will show both the reduction and give an idea of how the lower bound works. Okay, so I hope the outline is clear. I'll go on to define now what is this pointer chasing problem.
Rakesh?
Yes.
So what about the upper bound? Do you know if anything you can do? Is it believe that you can do anything non-trivial if you have more than 2 rounds?
So I think it is believed that omega n log n is the expected lower bound.
Oh, omega, okay.
Even for unbounded rounds.
Okay. So this iterated log is an artifact of your proof.
More it's
That's the belief.
so we refer to a previous result and adapt it to the randomized setting. Our reduction and that result together gives this.
Okay.
It's not tight.
Okay.
Okay. So let me define the pointer chasing problem. This is in fact a slight variant of pointer chasing and say why than the usual one. So in this variant, the game is played, or the input is kind of a graph on a bipartite vertex set. So I'll think of it as graphs still, but directed graphs. Alice is given, so you have 2 vertex sets, V and VB. The size of both I will take as n. Alice is given a bijection from VA to VB. Bob is given a bijection from VB to VA. So you can think of these as directed edges. And these are bijections, they are not arbitrary functions. In a general pointer chasing instance and in literature, these can be arbitrary functions, but we need them to be bijections for our reduction. So we'll just deal with the bijection case completely. What is the goal? Well, there's a fixed vertex V0 in the left side, so let's call that VA, which is known to both. So V0 is known to both. It's a fixed starting vertex you can think of. And the goal, because this is a bijection, V0 maps to a unique vertex V1 via FA, which maps to a unique vertex V2 via FB. And there's a unique vertex at distance K from V0. Okay, in the union of the 2 bijections or matchings, as you call directed matches. And the goal is to compute this V. So because, for instance, Alice only has FA, knowing V0, she knows V1, but she does not know V2. Okay, and therefore she cannot immediately know any part of the remaining part of the graph. The same for Bob. Bob knows V0, but he doesn't know V1, so he doesn't know anything. So just a definition, we can think of this as a composed function starting at V0. Right? If I is even, then the last function is applied by Bob and it ends up coming backwards to VA. If it's odd, then the last function here is going to be applied by Alice. Okay, I'm going to call this version in which we're going to identify VK exactly. So recall that the goal here is to identify what VK is as a vertex. So it's not a Boolean function, right? It is a function, but not a Boolean one. It's the answer is log n bits. So I'll call this the full version. We will come to a slightly modified version of this soon. And just to kind of get this out of the way, that in pointer chasing, typically in literature, at the end of a protocol for pointer chasing, both players know the answer. Okay. Why I'm saying this and pointing it out, I will maybe come in a moment when we relate it to connectivity. And the version that we are concerned with is the bit version of this problem, as so it is called. In this, the goal is not to compute VK exactly, but just compute whether VK is even or odd. If you identify the vertex with numbers 1 to n. So is it the odd vertex or even vertex? So it's just one bit of VK that you want to find. Arbitrarily, it's the last bit. So I'm going to call it LSB of VK, or the least significant bit of VK. Okay. And clearly, this is no harder than the usual pointer chasing full version of the problem, because we could compute the full version, get just out to the last bit of it. Right? In fact, it's easier in some cases. So it has been introduced by Papadimitriou and Sipser, and typically this problem and many variants of it are used to kind of study rounds versus communication trade-offs. Good. So what is known about pointer chasing? Well, to start off with, there exists a simple k-round protocol that solves even the full version of it. What is the k-round protocol? Well, Alice knows V0. She sends Bob V1 because she knows V0 and knows the first function that maps out of it. Bob gets V1, he can compute V2, sends it back to Alice. This goes on for k rounds and they can determine what VK is. That's k rounds of communication. But now, suppose you slightly modify the question and say, I'm giving you k rounds, but Alice is not allowed to start. I want to restrict the protocols where Bob starts. Okay. So what does Bob know when he starts? Like, he knows V0, but he doesn't know where V0 maps to. Right? So there's no way he can use any, or it doesn't seem that he can use any useful information immediately that pinpoints anything about where the path is going to end up at. And therefore, the first round, if Bob starts the communication, kind of seems useless and no point. It's effectively like a k-1 round protocol, because the first step has to be taken by Alice using her function, right, out of V0.
Sorry, just to, for k equal to 2, for instance, so it's like you're just looking at 2 steps, is it?
Right.
Okay. And but now you're okay with 2 messages, but the first message must come from
Bob. In which case, suddenly Bob doesn't know what to do because he doesn't know V1. So we'll see that he can still send some useful information.
Oh, sorry, Bob's. I mean, if it was Alice going first and then Bob going next,
yeah.
The reason Bob is actually answering is because the assumption was that we want both parties to know what the answer is.
Right.
Yeah. I see. Okay.
Yeah, otherwise Bob will know
Bob will
he can stop there. But that's just convention that is used in pointer chasing. So we'll stick with that. So this quantity is of interest to us, and therefore I'll introduce this notation with superscript B denoting that Bob starts first, and superscript R meaning you have R rounds of communication. Yeah, I'm interested in the complexity of protocols that compute VK for some. Okay, so what's known about this problem? This has been well studied. The randomized complexity of the bit pointer chasing, that is finding the last bit of VK, is actually linear in n. So think of k as a constant. We do that for most of the talk. So thinking of k as a constant, the randomized complexity is like linear as compared to, say, k log n when Alice starts. So it's something like log n if Alice starts in k rounds, but if Bob starts in k rounds, it jumps all the way from log n to linear n. So that's a big jump, and that's what this series of results showed. But specifically for constant k, so this for a general k, this lower bound holds. For constant k, actually, Ponzio, Radhakrishnan, and Venkatesh showed a tight lower bound that for the full version, it's super linear in n. That's where the iterated log comes from. I'm not giving the exact log here. It's super linear in n. And, there's a small typo here. This should be the bit version of the pointer chasing. Okay. The bit version is slightly different from the full version when you restrict to constant. The bit version gives a superlinear lower bound. only if you're restricting the rounds to k over 2 and not k. So our adaptive lower bound comes from this result you mentioned. So this jump from like something like logarithmic to linear and to superlinear, that's kind of the threshold phenomenon with k rounds. Okay, good. So now that I've defined the problems, let me state what is the reduction level. So I'm going to say that if you have a protocol in R rounds that computes connectivity, okay, you'll get a protocol in R plus 1 rounds that solves the bit point purchasing problem. The R and R plus 1 is because the way I've defined it, be consistent with what's known before. In connector, only one player is required to know the answer for connectivity. In pointer chasing, you need one more round for both players. Okay, so that's the only reason you get an R and R plus 1. But normally, R round protocol for connectivity, it's R round protocol for bit pointer chasing. Okay, but there's a blow up in the number of vertices of the graph. The number of vertices on which you need to solve connectivity is like n times k. Okay. So using once we have the reduction, what we show, how do we prove our lower bound? We show that the randomized complexity of computing the least significant bit of V7 pointer, when Bob starts first and you allow 3 rounds of communication, is omega n log n. Okay. Why is it 7 here instead of say 3 or 4 that I discussed before? Well, we'll see that why 7 is needed. And this immediately yields from the deduction that the randomized complexity of any 2-round protocol computing connectivity is omega n log. Because k is a constant, so k is something like 7 for this constant bit for each. So our main technical result is this statement. Okay, and clearly we can also see what the reduction shows, that if you're allowed to show superlinear lower bounds for, say, you want to chase the 100 pointer, right? And you show that, in 5 rounds you cannot chase it, but 10 rounds or some constant number of rounds below 100 also you need, let's say, superlinear number of bits or n log n bits to chase it. That would still give you omega n log n lower bound for connectivity. If you restrict the rounds to be far lower than the pointer depth, as long as these are constants. And that's how when we adapt the Ponzio Radhakrishnan Venkatesh result, we showed it for deterministic. With some work, you can just say that it also works in the randomized setting. This follows. Superlinear lower bound for connectivity for any constant. R is always going to be the number of rounds. So there are 2 parameters here that I'll keep referring to, sorry. R is going to be the number of rounds of protocols that we're interested in. K is going to be the depth of the pointer that we want to chase. Okay, and typically we are looking at the regime here where R is strictly smaller than K. Okay, so let me go over give a brief idea of the reduction. So how does the reduction work? Well, in the reduction, Alice and Bob want to solve the bit pointer chasing problem. So they receive inputs which are perfect matchings, okay, of this form. Yeah. They receive bijections on a vertex set, okay, of size n each, and they know that they want to chase a k pointer. From it, they produce 2 matchings, okay, on larger vertex, such that if the least significant bit of Vk is 1, that is the answer to the bit pointer chasing problem is 1, then the union of these 2 matchings is going to form a single Hamiltonian set. Okay. And if the least significant bit is 0, then it will have 3 vertex disjoints. That's kind of what the reduction is doing. Okay. So maybe I will not give all the details, but this picture will be enough to give you an idea of what is happening. Okay, it's not very difficult given the picture. So recall that our bit pointer chasing problem had got n vertices on both sides. I'm going to create these blocks. Okay, how many blocks are there? They are going to be something like 2k plus 1 blocks. It's 2k plus 1. Yeah, roughly. Maybe for k equal to 2, I show. So maybe 2k minus 1 blocks. of vertices, and each will have two copies of the original vertex. Okay, so this here, this small rectangle here is like one copy of the vertex set from the pointer chasing instance. And how does the reduction look like? Well, these are the vertices. What are the areas? So each of these rectangle blocks here has a copy of V0 sitting in it. Okay, let's just concentrate on V0 and chase pointers from that by adding edges. Okay, so the edges that are added in this by Alice and Bob are the following. Okay, Alice adds her edges from, say, block 1 of VA to the corresponding vertices in the lower half. So there's VA prime and VB prime. What was going between VA and VB in my pointer chasing instance, she adds between VA prime and VB prime. Bob adds the edges going from this block to the next block. So what does this do? Suppose I want to chase the second pointer starting at V0. I know which block I'm going to end up in, right? I'm going to take a FA here and end up in block 2 of VA. Right? So you have FA followed by FB. Okay. Now what they do is, depending on what the least significant bit is here, you either map to the same block, same copy, or to another block. So maybe I'm not explaining this well enough. So you have two copies of V0 sitting here, depending on whether this ended up at a parity 1 vertex or a parity 0 vertex. It either maps to the same alpha block or maps to a beta block. After this point, they just invert their permutations. And they can do this because they know they add these edges independently of each other's in. So what does this effectively give us? It gives us that if the parity, let us say for k equal to 2, they're chasing the second point. So starting at V0, you have V1 and V2. So if the parity of the second step from V0 is equal to 0, then you end up, after all of this, back in the alpha block over here. If the parity is 1, then you end up all the way in beta block. Okay, because you switched at this stage if the parity was 1. And then we map it back so that it goes back to V0. Right? So the net effect of this is that if in the kth step they are hitting a vertex in this block with parity 0, then they map back kind of to an alpha vertex maps back to the alpha copy itself. Otherwise, it maps to the beta copy. You can see how this is going to create a cycle if the parity is 1, because the alpha copy is going to go all the way to the beta copy here, which is going to map back to the beta copy here, which is going to go all the way through this cycle and come back to the alpha copy. So the two alpha and beta copies will turn out to be in the same cycle. The parity is 1. If it's 0, then they turn out to be different cycles. So that's kind of the main idea. Notice that here we are using the fact that they are permutations and they are invertible when we want to add these edges. So this is where we use the fact. So our reduction uses the fact that we need bijections in the pointer chasing instance. Okay. So I'll skip the further details. These are just making this more precise, but I've just described what happens to V0. You can set up the other edges in a similar fashion, such that what happens is that you end up with either one cycle, if the parity at the kth block, the determining block is equal to 1 starting from V0, otherwise it ends up in more than 2 cycles. So I'll leave out this detail for clarity, but I hope at least the main idea is here. So using these permutations, I can trace paths so that I end up in a cycle with the alpha and beta copies. Alpha and beta copies die in the same cycle. Parity is 0, then they'll end up in different cycles. And we can modify this cycle. Now, a point of note is that these instances that, two matchings with Alice and so effectively Alice and Bob are producing connectivity instances where they have matchings. On this larger vertex set in case of the reduction, and the union of these matchings is either one Hamiltonian cycle or multiple cycles. So these instances were studied by Raz and Speaker in '95, and they show a deterministic lower bound of omega n log n on the communication complexity of electrons. Notice that these are not general connectivity instances. So therefore, the lower bound here is actually weaker than the more general connectivity lower. It holds for a more restricted set of instances. They study this in context of the log rank conjecture. Good. Okay, so now what we have established at this point is that there's a reduction from the pointer chasing problem to the connectivity. And the pointer chasing problem that you're interested in effectively is that you want to chase the kth pointer, but you have maybe far less than k routes to chase it. What can you do with this? Okay. It seems unlikely that you can chase the kth pointer with less than k rounds because by definition there's a composition of functions going on. But we'll see that there are some non-trivial upper bounds that can still be. So in particular, one can show that we showed this that if the number of rounds is at least k over 3, right? So you want to chase the kth pointer and I have something like k over 3 rounds, I can still chase down the last pointer, determine what vk is using just n log n bits. So if you want to transmit all the functions completely from Alice to Bob, that's like n log n bits, right? But yeah, with just k over 3 rounds, I can still do like n log n bits, I can find.
Is for all k or large enough k?
This is for constant k.
Just fixed k.
Yeah. So there's a k factor here in the protocol. It's actually nk log n. So it stops being useful beyond a certain small value of k. And for the big version, it turns out that in fact r over 4 rounds, k over 4 rounds suffice to chase the k one. And this n log n. So the protocols are adapted from previous protocols, and what I do is I give a concrete protocol for chasing maybe the 6th pointer, the bit of the 6th pointer using 3 rounds. Okay, so I'll describe the protocol. There are 2 parts to the protocol actually. So the target is going to be to find the least significant bit of V6. The 6th step in the chain, starting at V0. But I'm giving you only 3 rounds to do it. Okay, so how do we do it? And 3 rounds and Bob is starting, in fact. It's not when that Alice is starting, which may give a little advantage. Okay, Bob is starting and I'm giving 3 rounds. I claim that you can find LSB of V6. So how does one do this? So there are 2 parts to it. Kind of what they are going to do effectively is we are going to chase pointers from both ends. Okay, not just from V0. So naturally we think of starting at V0 and then finding V1 and going to V2 and so on. But actually, they're going to do this from both ends. This both ends thing works for the bit version of the problem. But for now, let us just concentrate on the forward part. You can ignore whatever is about the reverse chasing. We'll add it in later. So now Bob wants to send N1, right? So what can he send? He has a big global information about the function. Like he doesn't know what V1 is. Right? So what can he send? In M1, he's just going to send a restricted description of his function. Okay. So for every vertex in VB, so let me see. So for every vertex, he's going to kind of give the last log n bits of the vertex that it maps to under this function. So FB, this description of where 1 maps to is a log n bit string. He gives the last log n bits. Let's just stick to the forward chain. This is the forward part. Okay? I will describe the second part later. So clearly he does this for every vertex. So he's giving a partial description of his function for every vertex. Okay, so that's n times log n bits per vertex, which is n log n bits. Now, what does Alice do with this information? So Alice knows V1. Right? Now, what does she know after it? She knows V1 because she knows V0, and V0 to V1 is in her control itself. But V1 to V2 is in Bob's control. Okay. Now, what does she know about the neighborhood of V1, where V1 can map to? She knows the last log n bits of where V1 maps to, because Bob told it in the first message. Which means she knows the neighborhood of V1 up to a set of n over log n vertices. She knows that the next part, although it's Bob's function, because of his first message, she knows that it lies in one of these n over log n vertices. And so she sends to Bob as part of her second message the explicit mappings out of all of this of the function. Okay, she doesn't know where V2 is, but she knows it's one of these n over log n vertices. So she sends a log n bit description exactly of where these map to under her function. So now what does this do? Notice that this takes only order n bits. Okay. The blue ones are what Alice is sending across. She sends V1 as part of N2, and she sends the next neighborhood for all the potential V2s that she sees. Okay. Now at this stage, what does Bob know? Only 2 messages have passed. Bob has received the second message from Alice, but notice that he now already knows V4. Why is that? Because Alice sent him V1. He knows where V1 to V2 maps. Ignore this last one here. So he knows where V1, let me go back to avoid confusion. Yeah. So he knows where V1 to V2 maps because that's his function. He knows the exact map out of that because Alice has sent him. And the next layer is also in his control. Right? So after 2 messages, Bob already knows V4. Good. But recall that we want to compute LSB of V6, which is 2 layers down. So how do you find LSB of V6? So the point is you don't need to know V6 to find LSB of V6. So what they also do additionally, in the first round, Bob sends back where these vertices. So notice that V5 to V6 is in Bob's control. Okay, so he percolates back the bit information 1 layer. So he tells for every vertex in V5, does it map to a 0 vertex or a 1 vertex on the next layer? Okay, so he's kind of chasing the pointer backwards. He's doing it simultaneously from all vertices in V6. Okay, so for every vertex in V5, he's going to tell, does it map to a 0 vertex or a 1 vertex? Alice does the same thing again for the next, which means that by the time Bob knows V4, he knows exactly in 2 steps does it map to a 0 vertex or a 1 vertex. And notice that transferring back these parities takes only order n bits. They don't determine the identity of V6, but they determine the least significant bit of V6. Okay, because in 2 messages, they can just calculate the bit information back. Good. So I hope at least the general idea is clear that, once the point here is you can do a more general version of this, where you just chain together this protocol in blocks, right? In which in each step, you gain a look ahead of 3 because you have, your function, the potential at the next step, but that was already communicated. And then again, it's your layer. So, 3 steps together. Okay. So I won't describe this in more detail, but the previous example should kind of suffice to give you an idea of this.
The way you choose parameters there was you didn't choose it as optimal as possible because there was some lopsidedness in the.
There's some lopsidedness. You could maybe do a slight bit of gain levels because there's an n log n here, but the remaining messages are all order n. So there is a slight lopsidedness, but it doesn't
give some lower order.
Yeah, it gives some lower order. Okay. So notice that a 3-round protocol in n log n bits of communication makes Alice and Bob, possible to determine the least significant bit or the parity of V6. So the V6 is even or odd. And you can chain this together in blocks to get a lookout of 3 in every step. Okay, so I won't go over this detail. It's relatively natural to do. The same thing repeated again and again in blocks of 3. And now, what we will show, which is the main result, is that in 3 rounds, if you wanted to compute the least significant bit of V7, the complexity jumps from what was n log n for V6 to n log n. So this is kind of the main thing. And yeah, I will give you hopefully a good idea of how this works. Okay, so this is the main theorem that we target. Now, one thing to note is that when I'm describing the lower bound, okay, we are going to kind of think of every layer of the vertices as being distinct. Okay, so the way I described the pointer chasing instances, you had only a single FA that goes between two vertex sets of size n, and you did FA of V0, FB of FA, and FA of FB of FA. Here we are doing a slightly different construction or the instance where you have n vertices at each of the k layers, and then you have FA, say FA1 here, then FB1 here, then a different function from V2 to V3, a different FB from it, but these are equivalent because we're looking at constant k. So if you set all the FAs equal, you get back the original instance. And otherwise, this is a sub-instance of the original one because you could partition into blocks of n over k and do this. K is a constant. So we'll work with this. Okay. So how we show this? We use entropy-based techniques. So to start off with, we do the natural one. We want to show a randomized lower bound. So Yau's min-max lemma. We start with a distributional complexity of this problem. We consider a uniform distribution of the inputs, and we show that any protocol that communicates, say, epsilon n log n bits for a small enough constant epsilon should be making significant error over the space of the inputs. So what's the kind of protocol we are considering? Well, first of all, Bob sends M1, Alice sends M2, but at the end of M2, Bob should know the answer of them. Okay, and it is this answer. So at the end of M2, for instance, he knew what V4 was. Right? And it was this that he transferred back to Alice in the third round. Right? So the third round is kind of a dummy round in some sense. It just exists for both of them to know the answer. The first two rounds are the crucial ones, so one of them determines the answer. So without loss of generality, a protocol is going to follow this. At the end of M2, Bob should know the answer. So let's start it. Okay. So the first step in the proof is to show that any randomized protocol that computes, or effectively show this, we don't exactly need this statement, but to effectively show that any randomized protocol that computes V5 completely, not just the bit version, takes omega n log n bits. And then use this with additional work to show that Bob will not know the least significant bit of V7. Okay, so till V5 they cannot compute exactly, and V7 they cannot compute the LSB also. So those are the two general parts. For this talk, I will more or less concentrate on part one, try to give an idea of what are the kind of subtleties involved in proving this. And for part two, I'll give you maybe just a general outline. Okay. So how are results proven in pointer chasing? It's done by round elimination. So what does round elimination mean? Round elimination basically means that typically you find statements of the following form. You fix, so suppose there's a protocol that solves the problem with some desired number of bits. Right? You fix a M1 and B1. Why are we fixing B1? We'll see in a moment. Right? You fix a message M1 and a good V1, so that the entropy of V2 is large. Then you fix a second message, the second message and a second vertex, such that the entropy of V3 is large. And this process goes on until at the end of k rounds, if you want to show that the entropy of Vk is large, and therefore Bob cannot figure out what Vk is. So Alice cannot figure out what Vk is. The use of what is the reason for fixing these V1 and V2 over here? Okay, so if you're familiar with communication complexity, then you would know that one typically considers this rectangle structure of the inputs. You have Alice's inputs over here, indexed here, Bob's inputs indexed here. Now, when Bob sends a message, say M1, it kind of, you're looking at a sub-rectangle formed by this, vertical cut. Okay, it's a partition of the inputs into 2 raised to n1 places, and you're looking at one particular, slice of. Now, within this subrectangle, further, if you fix V1, now notice that V1 depends on Alice's input, and therefore it's a horizontal cut. So when you do this, what happens? You're going to look at this particular subrectangle where V1 is fixed. And once you fix V1, you try to show it becomes easier to analyze the error. And similarly, now you fix M2 and V2 formed by a horizontal and a vertical cut respectively. And now to show that, the entropy of V3 is large, you look at this rectangle. And we say that in this particular rectangle, which is typical for the protocol, the entropy of V3 is large, and therefore they should make errors. So it turns out that these kind of rectangles do not work when you want to chase, say, the 6th pointer using just 3 rounds. Okay. So what we will do is basically choose different subrectangles, slightly more involved subrectangles, that will allow us to still compute the error. Okay. Typically, if you thought of it, there was no reason to fix V1 and V2. One could have directly analyzed the subrectangle formed by M1 and M2 and try to bound the error in that. But fixing V1 and V2 gives you some handle on how to bound the error. Okay. But just fixing V1 and V2 for us does not work, and we'll have to do something slightly different. Especially when you're communicating epsilon and log inputs. Okay. So what do we do? Our first step is still like the origin quantity. So what I'm going to describe is why you cannot compute V5 using just 3 rounds of communication.
Is this a black box claim? It should be, but let me say, if you have a lower bound for PC and K, then you have a lower bound for BPC and K plus 2.
If you have a lower bound for PC and K, no, it's not, because the number of rounds determine how far the depth is. So it's K over 3 versus K over 4. So it's not immediate anyway. So if anything, there should be a manipulative factor there, not additive one. Even that, I don't think it's real. It's not a black box direction. Okay. So we first fix I1. So let's go into some amount of proof detail. I think if I can do this. So let's find M1 and V1 such that the entropy of V2 is large. This is still like old pointer chasing. First V1, I'm going to fix. So when I say fix in terms of a lower bound, there's a protocol, and I'm looking at a subrectangle. And I can point to a subrectangle using entropy techniques where the entropy of V2 is still large. Okay, but M1 and V1 are fixed in the subrectangle. So this is what the subrectangle is. Okay. Now, what do I know about this? Right? The entropy of V2 is large, means what does the entropy of V2 look like? So notice that H, the entropy of FB of V1 will look something like 1 minus epsilon log n. Okay, we'll see why this is removed. Which means that the number of possibilities for V2 is something like n to the 1 minus epsilon. Recall that the protocol was transmitting epsilon in log n. So with every message of the protocol, the entropy of the functions will drop down by epsilon in log n. The entropy of average coordinate drops down by 1 minus by epsilon log. Sorry. Okay. And at this point, the difference that we do from previous work is we do not fix V2 to analyze what happens at V2, but rather we say that we are going to fix a set of possibilities, a set of mappings out of V2 such that V4 is really spread out. Okay. So notice that under this fixing, if you fix V2, then V3 actually has 0 entropy. Okay. But allowing V2 to vary, I'm going to directly jump and analyze what happens at V4. Okay. And that is what is going to. Yeah. So how am I doing on time by the way? 10 minutes. 10 minutes. Okay. And we'll show that in this resulting subrectangle of inputs, V4 is close to uniform. Okay. We'll see why this is. And the key point is to show that most of these assignments that we can fix are going to be good. Okay. So when I say fixing something as part of the input, it means I'm looking at a subrectangle which fixes that sigma. And I'm going to analyze that particular subrectangle. So there are certain subrectangles corresponding to good sigmas in which I can bound the error. Okay. And the fraction of these sigmas are large, so overall I'll be able to bound the error. Okay. And this is the main outline. What we're going to say is that once Bob sends a message, right, for most subrectangles where sigma is fixed, right, what is Alice going to see? Alice is going to see that V4 is uncertain in an omega n side set. Okay. So this is just after the first message. Alice is seeing that the set of possibilities for V4 is like omega n size. What can she possibly do to tell Bob about V5 in the next step? She can't do much because she has only epsilon and log n bits. Bob should know V5 exactly out of it. So she cannot effectively communicate what is V5 out of all of these omega. It's like an indexing problem. As we said, if you've heard of the index problem, it reduces to something like the index problem, right? And this is what ensure that Alice cannot communicate because after the first message she sees omega n at V4, she cannot effectively communicate V4. So showing this takes a bit of work, and let me maybe not go too much into the detail of this. I had a few slides, but turns out I'm a bit short on time. So Bob cannot predict V5 after receiving M2, and that would mean that this is omega n. Now, what is the difficulty in showing this? So there are some subtleties that are there when showing this. This main subtlety that one needs to figure out is that when you give M1, the functions FB2 and FB1, the function FB that is there between V1 and V2 and V3 and V4, they become correlated. Okay. And somehow handling this requires a bit more work. Okay. If they are a product, then it's slightly easier, but because they are correlated, we need to account for. So every time Bob sends a message, in this case, there's only one message. When Bob sent a message, it correlated all the FBs. Okay, so because it said that for some FBs that occur here, only certain FBs can occur. Okay, and one needs to be careful about handling this. So unfortunately, I cannot go into that. So let me not. There's some proof details of how one does this. In particular, showing that when is a potential I reachable. So, let me kind of skip the details in interest of time. Yeah, I'll be happy to discuss it offline. So effectively what we show for the randomized version, so what I said just was intuition about the deterministic version, what are the V4s that Alice sees as potentially reachable? And that's omega in size, and therefore she has to send information about all of it in the next message, which is clearly not possible. Like the randomized version of this is that for a good fraction of M1 fixings, V1 fixings, and sigma fixings, there's a set of size something like say n over 400, V400 is a so size n over 400, such that the probability that V4 is equal to I is like omega 1 over. So this is like being very close to the uniform distribution. You have omega n elements, each of them is being hit with potential of being V4, the probability is 1 over n. So when Alice is looking at this, she's seeing, look, all of these omega n elements are maybe equally likely to be V4. I don't know what to communicate about this because I need to communicate what the next step is exactly to go. Okay, and in fact, what is going to happen, in fact, I can see just by a small subadditivity of entropy, one can see that for a good fraction of these vertices actually, because Alice can send only epsilon and log n bits, Bob will see something like n raised to 1 minus epsilon possibilities for V5 out of many bits. It's not that Bob just doesn't know V5 up to like 1 or 2 vertices, but he doesn't know V5, the V5 can lie in some n raised to 1 minus epsilon possibilities out of all of these vertices. So it's really uncertain. Good. So and this is what we use for the big version. So till now what I've described corresponds to the fact that the Bob cannot determine V5 exactly. Right? So what does he see? Right after the second message, he sees V0, V1, V2 all the way till V4 because Alice has given him sigma, or rather we are fixing sigma in that subrectangle. And he sees all the way till V4, but out of V4, he sees many possibilities and he cannot predict what this is. Okay, so V5 is unknown to Bob, but is the parity of these V5s also going to be unknown to Bob? And actually not, because we have seen a protocol that computes the least significant bit of V6, in fact. Forget V5. The upper bound, you have an n-log protocol for computing LSB of V6. So clearly there are protocols in which, even though V5 is not clear, the parity of V5, where what the last bit of V5 is clear. Right? Okay, and that's because of this backward pointer chasing. But that's why we need to go to V7 and say that the parity of V5 is unclear to Bob. It's maybe clear to Bob, but parity of V7 is still going to be unclear to Bob. And how do we show this? Well, we fix subrectangles by percolating things. Okay, exactly like in the upper bound. Okay, so if you look at the upper bound, basically it's that same intuition that we're going to follow and mimic when we're showing the lower. So what is this intuition? It says that look, the parities at the last layer, which is what I want to determine, are fixed. They are a fixed function, irrespective of the inputs of Alice and Bob, because that is the least significant bit of the vertex at that layer. So it's either even or odd. So this coloring, think of it as a 2 coloring of the vertex set, which gives the final answer. That is fixed. If you hit this vertex, I know the answer is a 1. If I hit this vertex, I know the answer is 0. This is a 1, this is 0. But what about vertices here? Where does this vertex here lead to? Does it lead to a 0 vertex or a 1 vertex at the next layer? Well, that depends upon FA4, the function that Alice has. Right? If I look at this as a coloring chi, the induced coloring here based on Alice's function can be given as a composition of that chi and FA. Right? And if FA is random, this coloring is random. Right? And now what happens over here at the next layer? Well, it's one more layer of randomness added in by Bob's function. So Bob sees that, this is delta of V4, the shadow of V4, so to say. He knows V4, he knows the shadow of V4, which is like the n to the 1 minus epsilon potential V5 values. And possibly he knows the coloring here, but due to the randomness in FP3, he's going to kind of see an unpredictable coloring of this set. So that's the intuition. As I vary FA and FB, I get unpredictable colorings at this, which means he cannot say whether the parity of V7 is going to be 0. So you need the randomness in the next 2 layers to percolate. Okay, so this involves showing that the LSB of V7 within the shadow or within the potentialities of V5 is close to balance. That, depending on the random functions given to Alice and Bob, these could turn out to be balanced as 0. Okay. What do I mean by balance as 0, 1? Where does this vertex in the shadow lead to? Does it lead to a 1 vertex in 7 or does it lead to a 0 vertex in 7? As you vary FB and FA, this answer varies close to balance across the set. Okay, so this is the informal lemma. So for this, we need to work with compositions of high entropy functions. And this is kind of the informal statement of the lemma. I also put a formal statement because I think it's maybe of independent interest. So for a typical chi6, which is a typical coloring at this layer, and a high entropy FD here, the composed coloring looks random to Bob, even if you restrict it to small sets. Okay. So if you fix this coloring, the intuition is if you fix this coloring here of the vertex set into 1 and zeros, okay, the randomness in FB is so high, it's like 1 minus epsilon n log n, that it guarantees that Bob sees that the paths that lead to 0 and 1 vertices are kind of balanced, even when you restrict it to this n to the 1 minus epsilon. So which is why he cannot predict, does it lead to finally in V7 a 1 vertex or a 0 vertex. So that's kind of the idea. And this means that he cannot guess the least significant bit of V7. Okay. So this is just the formal statement of the lemma. I think it's useful to maybe just look at it once, what the formal statement says. It says that if F is a, so this is just a statement that's independent of everything that has happened before. The statement about composition of random colorings with a high entropy function. What this says is that if F is a high entropy function here, chi is a balanced coloring. Over here, why balanced? Chi is a balanced coloring over here. 2 coloring, balanced 2 coloring, I should say.
You're not even talking about bijection.
No, here we are talking about bijections.
So random function is random.
Actually, here we don't need the fact that there are bijections. Yeah. So the entire pointer chasing proof does not strongly require the fact that there are bijections. Yeah, the reduction requires the fact that there are bijections. But this part here, it can be a random function. All we need is that it has 1 minus epsilon in log n. Right. Okay, then what it states is that there exists a subset of this vertex set. I mean, that subset is omega n sized, such that if you look at the composed coloring on this, it will be random. Okay, and how do we determine randomness of a composed coloring? When you pick any small set, and that set should be kind of close to balanced color. Okay, so this idea of being close to balanced color and composition is actually there in Ponzio, Radhakrishnan, and Venkatesh. They show a similar composition lemma, but in their case, they need to color much larger sets, which means they need less random colorings. For our case, you see that the neighborhood potentialities are like n to the 1 minus epsilon. So we need to color smaller sets. So that's why we need to do things slightly differently. Okay. We say that for all distributions on this set, with mean entropy at least k, mean entropy greater than k is just a proxy for the set size being at least 2 bar k. So for large enough sets, the composed coloring is close to balanced. This is the balance of the coloring. How much di times xi is the coloring, then di xi differs from half. Yeah, goes down in some way. The parameters are not all that important. The fact is that the probability over this will be 2 columns. Okay, so I think I'll stop here. I'm out of time. So future directions, the obvious question is, of course, the big open question is settling the randomized complexity of connectivity. But at least this gives us some starting point for showing lower bounds against, or tight lower bounds against bounded ground protocols. And in general, the other question that has not too much been explored is tight bounds of pointer chasing when you have unbounded bounds. We are looking at this pointer chasing where you have the number of rounds is far less than the depth to be chased. But what happens if you allow like unbounded grounds? Will you require k log n or can you do better? That is something that is I don't know a direct application of it, but it seems interesting to think about. You see, both are problems where the depth of pointer you want to chase is far different from the number of rounds. Let's stop here. Thank you. Sorry for being a couple of minutes over.
Question. Where does the iterated log come from? I mean, like, in the argument where.
So, you saw the log n bound.
Yeah,
right?
okay. But what would happen if you had more?
So it turns out that if you have more rounds, you can do. So there I allowed 3 rounds to chase. But if you allowed, say, 4 or 5 rounds to chase B6, then you could do log n.
Oh, I see.
You know, the log n was set because of these certain parameters. But actually, the more general protocol from where it is inspired by is the DJS protocol, and they do the iterated log upper bound to chase. Okay. But then, if you want to chase a k pointer, Bob starts, but you're allowed k rounds.
Yeah, let's start.